Okay, so we're going to continue this talk about differential calculus, and we'll be talking specifically about stationary points. Okay, here's the list of vocabulary words that you're going to need to know. Stationary point is this. A stationary point is the same as a critical value. We referred to critical values or critical points before, and we'll talk more about what those are. We have something called a global maximum, global minimum, local maximum, local minimum, and a stationary point of inflection, which we'll talk about as well. Okay. All right. So what is a stationary point, and what is a critical value? Okay. A stationary point is basically a point on a function when, if I take the derivative of it, I end up with the value of 0. Okay. So let's interpret what that means. It means that the slope of the tangent line at a certain point is 0. Okay, so that means where on this graph would that be? Okay, you could see that there's going to be a stationary point here because the tangent line has a slope of 0, and here. Okay, now it's obvious here that this is a hilltop, right? It looks like a hill, and so we could say that that is a local maximum. That's exactly what it is. This is a local maximum. Okay. Right here we have a dip, and then it decreases and then goes back up, so that is called a local minimum. Okay, I'm just going to abbreviate here. Now, just because the derivative is always 0, it doesn't mean that that value or that point is necessarily a maximum or minimum. We'll see later a case where you could still have the derivative be equal to 0, but it's not either a maximum or a minimum. It's actually something called the stationary inflection, and we'll talk about what that is. Okay, so let's take a look at this graph. Whoops. Let's take a look at this graph. This is restricted on the domain from -5 to 6. Okay, so this right here, it's called a local maximum. Also, in some books, you might see it called a relative maximum, okay, or a relative minimum. Okay, but our book goes by local maximum, so just be aware of this other term. Okay. Over here we have an endpoint that is bigger than our local maximum. If you look at all of the local maximum and the maxima and the endpoints, whichever one is highest is the global maximum. So that's a global maximum in this case. Okay. Is it always the endpoint? Not necessarily. Okay. It could be that you have a shape that looks like this. Okay. Then this would be my global maximum. Okay, global max. And in that case, it would actually be a stationary point. Okay, it would be the same as a local maximum. Okay, so that's a local, well, that looks terrible, but that's a local maximum, and at the same time it's a global maximum. So you could have a case like this. Just in this example, we have the global maximum on the endpoint. So you do need to consider for global, you need to consider for these guys, you need to consider the endpoints. Okay? All right. So there you have it. We have 3 types of, oh, sorry, this of course here in this example would be a global minimum. Okay? So just to recap, a stationary point or a critical value, those are the same, those are synonymous. Okay? Critical point or a critical value. A critical point or a stationary point is a point on the graph where the derivative is 0. Okay? And it could be a local maximum, local minimum, or stationary inflection, and we'll talk about this a little bit later. Okay, so what is a stationary point of inflection? There's 2 ways of spelling this, by the way. This I think is a little bit more British or European, maybe Australian. I'm not sure, but this is the more American way of spelling it. Okay, a point of inflection is a point that has a derivative equal to 0, okay, at that point, but it's not either a maximum or minimum, and it looks like this. Okay, so here we have a point of inflection. We call this stationary because later on we'll talk about what a non-stationary point of inflection is, but just for now, know that a point of inflection is when you have a derivative equal to 0 for stationary points. Okay, so it's increasing, it stops, and then it increases and increases. So on either side, we have a increasing on this side and increasing on this side, but the slope of the tangent line is 0 at the point of inflection. Okay, and here it is. F of x equals x cubed. F prime of x is 3x squared, and the derivative is 0 at the point x equals 0. Okay, the sign diagram would show positive, positive. Okay, so you would think that, don't think that just because the derivative is 0 that it is necessarily a local max or min. Okay, and so here's another summary of that. We have a local maximum here, okay, a small hilltop, a small valley, okay, that's a local minimum or a relative minimum, and we also have a stationary inflection. Okay, right here you can see that the slope of the tangent line right at that point, the line is horizontal, so the slope is still 0, just like it is here. Okay, so it's still 0 on all of these points. So all of those are called together stationary points or critical values, and this is an example of the sign diagram. Okay, increasing, decreasing, negative derivative, positive, positive, positive derivatives over here. Okay, so this is a visual way to look at it. You don't have to always graph it. If you look at just the sign diagram, you can figure out whether it's going to be a local maximum, minimum, or stationary inflection. So if I were to just look at the sign diagram and I see a plus minus, just visualize that it's increasing then decreasing. Okay, it's increasing then decreasing, so I would expect to see a maximum there. Okay, same thing with a minimum. It's decreasing, and then at my f prime of f prime of a is 0. You know, you'd expect to see, if I start to see an increase again, you'd expect that would be a minimum. Okay, and same thing with the stationary inflection points. Okay, if I have increasing and then it's increasing still, you'd expect that would be a point of inflection. Decreasing, decreasing, you would expect that to be a point of inflection. Okay, so hopefully that is a good summary. This chart is also in your book. Use that to help you study and to remember what these are. Okay.